Okay, while we wait for everyone to be seated, Patrick Lauer will talk about Postgres and scaling it with lots of data. So please take it away.
Let's give people a second to sit down. Okay, hello, I'm Patrick. I've stared into the abyss, so hopefully you don't have to. I want to talk about especially Postgres, but I think most of the issues you have with other databases roughly the same. About me, I'm currently working at a small company called Credative, about 2 years now. I currently work in a database team, mostly Postgres, but we also have other stuff. MariaDB, sometimes Kafka or Elasticsearch. It's all good fun. Originally, I come more from the sysadmin side of things, and I kind of accidentally fell into the database part. In my spare time, I'm also a Gentoo Linux developer, but that's mostly unrelated. 1 minute of marketing. Credative is a relatively mature company, founded 1999. We have about 40 full-time engineers available if you have any troubles. We do in the widest sense open source, but of course we have a focus on things, for example, Debian, Kubernetes Proxmox, databases mostly Postgres. But if you have other topics, feel free to talk to us. Worst case, we say we have no idea and we don't think we can help you. And since 2025, we're an independent company again. In between, there was a confusing time where we were bought and the company that bought us got bought and everything was weird, but we're beyond that now. So a short overview. I want to talk about basically my history, why I talk about big databases, some of the limits in Postgres, some of the limits of hardware, and pretty much what happens if you put a lot of data into Postgres, which of course leads to interesting scaling issues. And I think that's the part that most people here want to hear about. Just a question. How many of you are currently managing any databases? Most are. Okay. How big are your databases? More than, let's say, 10 gigabytes? Less hands already. 100 gigabytes? A few hands? A terabyte? 10 terabytes? Okay, there's still a few crazy people here with more than 10 terabytes. I think we should have a talk later. This is a range where things get really spicy. So how did I end up here? Roughly 2015, I started a new job, a little startup in Berlin. Was good fun. We were using Postgres as our main database, and we saw this talk by this nice guy, Chris Travers, Postgres at 10 terabyte and beyond. And we said, this guy, he seems to know what he's doing. We should hire him. So we hire him. And like 6 weeks later, he's doing a talk, Postgres at 20 terabytes and beyond. Like, oh dear. Yeah. Then people ask, you have one database with 20 terabytes? Like, no, we have about 32 of them. Such is life. And then we ran into this stuff where like Elasticsearch didn't scale. Like you tried to put a petabyte in it, no. So we replaced Elasticsearch with Postgres because we managed to make Postgres scale into this range of petabyte or 2 or 10. There's not much public about that, so the only thing is in 2018, I think, my then colleague Victor held a talk about Bagger at PGConf Russia. We called it Bagger because here you have the big excavators in the Tagebau, Bagger 289. It's like, yeah, we're building that, just with data and not with coal. So there's Bagger. We built a petabyte-sized logging infrastructure because nothing on the market could do it. In the end, we were around like 10 petabytes when I left the company, and it was just a financial thing. And like, you want to store more data, we need more hardware. We had an internal thing that was basically statistics and such things, was like 400 terabytes or so, sharded over like 32 servers, and it continued growing. So I think it ended up with like close to a petabyte over like 64 servers, or I don't know. We had one setup with like 20 terabytes in one server, which is okay, but it was like 400,000 tables. It does work, but maybe it's not a good idea. We had one setup that was about 200 terabytes in a single machine, because we couldn't get bigger SSDs, so we could only put about this much data into one server. And that was basically just a sample of data for, let's say, fraud analysis. So it was just a small slice of our data, and that was already lots of data. And we always use Postgres as default because it mostly worked. Like if you really push it at some point, it's suspicious, but it went very far. We tried other things and they didn't work, so Postgres. We're not the only ones who are doing this crazy stuff. So for example, at the recent PGConf.de, there was a really great talk from the Adyen people, operational hazards of managing PostgreSQL database over 100 terabytes. And yeah, there's operational hazards. GitLab has done many really good talks at mostly PGConf.de, PGConf.eu. They have not so much the lots of data problem, they have the data is mutating fast problem, which is related but different. And Chris Travers has basically carried this whole topic forward. I worked with him for 5 years, I think. And he shifted to a slightly different topic. So I asked him if I could kind of inherit it. He said, yeah, it's fine. But he's still doing some interesting talks about lots of data. And of course, there's many more. I apologize for not listing all of them. But lots of people run into this region, and they have lots of fun. So basically, the lesson before anything is try to avoid having data. Lots of data is lots of problems, so just don't go there. Usually there's business requirements and things, so you have to go there, so such is life. So what are the limits of Postgres? Documentation says, for example, you can have 4 billion databases, where a database is basically a collection of tables and stuff. So within Postgres, database basically means a named thing that contains other things. So you could have like 4 billion databases. That's kind of very familiar number. That's roughly like 32 bits. It's unlikely that you hit that. Within one database, you can have like 1.4 billion relations, where relations are anything stored in the catalogs, or tables, views, sequences, indexes, and so on. I would say it's unlikely that you hit that limit. And if you look at the number, it looks like 30 bits. Like, it's interesting how the bits are used here. So on paper, it should be fine. It's unlikely that you hit any of these problems. Rows per table, this is surprising. It's limited by the tuples that fit into 2 to the power of 32 pages, which is roughly 32 terabytes. If you have 8 kilobyte block size, you could use a different block size, but there be dragons. I recommend not doing that, but feel free to do so. So 32 terabytes in a table, that's still pretty big. Most people, most of the time, are not going to hit that, but we're here because we're doing things outside the normal range. But basically, the mechanical limits within Postgres they're basically so big, I would say it's not something to worry about. There are some other limits that might be more annoying. So for example, you can only have about 1,600 columns per table. Well, with 8 kilobyte block size, you could use bigger block size, but trade-offs, don't go there. Any single field is limited to about 1 gigabyte in size. That's due to what Postgres calls TOAS, the totally oversized attribute storage. There's a question, why do you put such big things into the database? But people do. One really weird thing is that JSONB, which is a slightly optimized JSON storage is limited to 256 megabytes because it has to escape things. And the escaping means, worst case, it grows in size, so it's even smaller. So this is something that I've heard people complain about. Hey, there's large objects. They can go up to, I think, 4 terabytes. Please don't do that. Large objects don't have a good interface. It's basically like a file handle where you seek, and it's not fun. Please don't do that. Large objects, no good. There's other limits, for example, the shared buffers. So basically the data that Postgres caches itself is limited to about 256 gigabytes. So if you have infinite RAM, Postgres might still be limited to a kind of small portion of that. And again, with 8 kilobyte block size, please don't change the block size. It's so seductive. Oh, 64 kilobytes. Yeah, no, please don't. So I would say there are relatively strict limits on the shape of things we can put into a database. Like you have this 1 gigabyte limit and all that, but the number of these things that we can put into the database is roughly unlimited. So at a first glance, we're good. We can put any amount of data in and it should work. Okay, hardware limits. How much can we even put into one thing, like one server or one instance? So modern servers can get pretty big pretty fast. So 256 CPU cores, 4 terabytes, that's easy, not cheap, but just go to whatever, Dell, HP, Lenovo, they all ship it. IBM, no issue. On large systems, you might learn some interesting lessons about things like NUMA, non-uniform memory access. There's a great talk from Andres Freund at the PGConf EU about that last year, 2024. These large systems behave in counterintuitive ways. So maybe it's not so awesome. And the storage, basically, if you have the money, putting like 6 terabytes into a single server is easy, not cheap, but easy. And you can just attach some network storage, and basically there's no reasonable limit. Hundreds of petabytes, whatever. Mostly limited by how much money you're willing to spend on this. And there's always a question, does it really make sense to have a single system that big? I mean, maybe it's cheaper to have multiple smaller ones. Something you need to figure out. If you really want to go big, the biggest system I'm aware of, maybe there's something bigger, but biggest I'm aware of is the IBM Z17 mainframe, which in this maximum configuration is about 4 or 6 racks wide. And you can get 208 8-core CPUs, that's over 1,000 CPUs, running at 5.5 gigahertz. Nice, nice. 64 terabytes RAM, that should be enough. So there's no public pricing on that, so I've heard suggestions, ideas. This is roughly in the dozen million euro range, somewhere around that. Is this really a good idea? I mean, I have opinions, but you could do it. So now you say, hey, let's split this all up into many single things. That's cheaper maybe. So somehow we distribute the data. So the easiest thing is to use application sharding. So your application somehow knows that this data goes there and this data goes there. And then you try to grow the whole thing and everything is pain. And application sharding is not very economic. And you can't do complex queries. I mean, you can, but it all gets very quirky. There's many things within Postgres, for example, Citus and pgdog, that give you some kind of sharding, so you distribute over multiple machines. Greenplum Cloudberry DB, that's more towards analytics. It's kind of specialized. PostgreSQL, PostgreSQL are, as far as I'm aware, dormant, but they were basically the original projects that tried to make Postgres run distributed. And all distributed systems are somewhere in this trade-off space. Either they're slow in quotation marks, because consistency needs to percolate through the whole system. So you have the network latency, the storage latency of the other node, and everything takes time. Or you lose features like it's not atomic, it's not consistent, it's not isolated. Or like the most common one, it's not durable, it's fast. You know, benchmarks like, yay, but yeah, dev null as a service. So here you're in this weird trade-off space. What do you actually want from your system? Do you need this relational, structured thing? And these requirements decide what you should do. So I'm not going to say, like Citus is awesome, you should use this. I'm asking, what problem are you trying to solve, and which of these options works for you? So sharding, for example, Citus is fascinating because you just run Postgres, you kind of connect a coordinator and the data bits, and now you have Postgres running over 30 servers, but it doesn't have global synchronization, which makes it relatively fast. But there's this quirk or feature, however you want to look at it. A transaction might be partially visible because on one node it has already committed and on the other it hasn't, and the speed of light means we're in this weird space where things take time to move through the system, and depending on when and where you look at it, things are weird. So it's kind of eventually consistent, but is that really something you like? I mean, does your data allow for that? Does your usage of data have this, take this feature? Application sharding is horrible because now you have to emulate the transactions somehow outside of the database, and everything is frustrating. There are things like two-phase commits, but they tend to be relatively slow and complex, and it tends to do weird things. And now performance, every query has at least a network latency, which is non-zero, plus sometimes multiple round trips through different systems. And you might even have a single component overloading while the rest is not yet so busy. So you have the theoretical performance and what you practically can squeeze out of it. And those two can be wildly different. So now we're in the space relational database without ACID. What are we doing here? Why not use some NoSQL solution or something else? So why are we still using Postgres? So this is a very weird space where, for example, you say we use Postgres because we're familiar with it. But in this space, everything is weird. So one lesson there is a lot of problems can be solved by throwing money at them. Big data, big budget. Not all of them. Sometimes even money can't fix the laws of physics for us. And even with a lot of money, if you don't have the tooling to actually use it, it doesn't really help you. But it's expensive if you really have lots of data, so maybe you shouldn't have that much data. Slightly tangential, but having worked in this weird space, I've noticed, I've seen this labeled as normalization of deviance. So basically, you're doing weird stuff and you get used to it. So you reach this point where this is normal for you. Like, yeah, I always have to kind of kick the stove here and pull on this lever to get the gas started. That doesn't sound right. But you're doing it every day. You're so used to it. So you're like, yeah, that's just how it goes. So you're in this, you talk to people at a conference and they all have this look on their face and it's like, did I say something offensive? So there's stuff like, and then we disabled fsync to make it run faster. Yeah, it's a choice, but you can run into the space where best practice just doesn't work. Like it doesn't make any sense. So the best practice rules are out of the window. So what are your rules? And you make it up on the spot. And hey, it's an append-only workload. Let's disable auto-vacuum. Yeah, you shouldn't do that. But at that point in time, it made sense to try to do it, and we learned many good lessons. And Chris Travers gave me this rule of thumb. Every time you grow a system by 1 order of magnitude, some components will become a bottleneck and not scale with it. Problem is, before you can't predict, well, sometimes you can kind of guess, but you can't really predict where the bottleneck happens, so you can't plan a system to grow to the size. You need to start small and then adapt and figure out where the pain happens, and then try to fix the pain. I'm not aware of an engineering strategy that allows you to build a system, let's say, scalable 1,000 times more. You always find weird things that shouldn't happen, but they do happen. So you end up with this observe, adapt, adjust, try to fix it, and hopefully it works. But it can be, let's say, unpleasant. So Postgres with many data. So there are some practical limits that are not directly Postgres. For example, there's a great talk from the PGCon 2013, billion tables talk, where these people had the idea, hey, what happens if we just create a billion tables? And you say, yeah, should be easy. And the biggest bottleneck for them was that the file system doesn't like billions of objects created. And they split the whole thing into multiple file systems to kind of shard the data so that the file system survived. So Postgres itself is fine, but the underlying abstraction, like the file system or memory management, just go weird. One other thing is velocity, so the rate of change. The write-ahead log in Postgres is basically a single mutex. It's a single serialization point, and practically you're limited to like 1 or 2 gigabytes a second. Depends on the setup, maybe a little bit more, but that's basically the limit, how fast you can mutate data within a single Postgres instance. You can't really go much faster. So this kind of limit means you want to put a petabyte into Postgres. That's like a million gigabytes. That's going to take like a million seconds. That's like a week. So if you have an empty database, you fill it up, that takes a week. Is that okay? I mean, maybe it is fine. Maybe you say, no, we need to do it in 1 day. Then it's not going to work. And even small databases can be painful because, for example, they have a very high rate of change and long-running transactions. So all kinds of weird things start to happen, and your queries do strange things. Your tables grow in size. Your data is small, the tables are big. Everything is weird. So size is usually a good metric. The bigger, the more pain. But depending on the workload, even a tiny database can be horrible. And best case, you have both in one database. It's big and mutating fast, so then things get exciting. So if you have a small database, I'm saying here 1 gigabyte fits in CPU cache because some of the AMD EPYC CPUs actually have a CPU cache of over 1 gigabyte. Technically, but it's kind of split, so it's not really 1 gigabyte that you can use like that. But CPUs already have this much memory, so basically it shouldn't be a problem. Stuff like backup restore, in an instant alter table, second or two, everything is easy. And usually you have like a handful of tables and like 3 indexes. You can keep track of that by hand. Like this is still human scale. Life is good. So now you grow to, let's say, 1 terabyte. So most of the time that doesn't fit into RAM. I mean, you could get a terabyte of RAM, but most of the time you don't. So now accessing data means accessing the storage. Storage tends to be glacially slow, so this is causing some irritation. If you haven't done any tuning, you don't have any indexes, most likely, which means every access is a table scan, so you read the whole table to find anything. That tends to be slow, so you maybe need some indexes. If you add too many indexes, and for example inserts and updates get horribly slow, so don't add too many, but don't have too few. This is kind of an art, figuring out what's the right amount for your workload. And again, I'm not going to say this is the right amount. I'm saying For a specific workload, you need to figure out what works for you, what is needed. Postgres specific auto vacuum at this size starts to get a bit weird and quirky, and the defaults are very conservative. Postgres is very polite. You most likely need to change defaults and carefully tune things without overloading the system. So finding the right balance is again a bit of a game. You need to test a bit, but where's the fun if everything just works? You can do some performance tuning. For example, if you have many updates, you decrease the fill factor, so every page has some free space. So if you do an update, it can happen within the page, which is hopefully more efficient. You can change some internal, like the tuple cost, some internal metrics. Hopefully the query planner enjoys that and does better plans. You might want to tune the checkpoint behavior. Again, that's very Postgres specific. If you do query tuning, Postgres has a slow query log. That's usually a good starting point. And explain tells you what a query is doing. That's basically the magic trick. You stare at it, then you try something, and you do that in a loop until happy. There is an auto-explain extension which does the explain for every slow query, which means in the log you see the query plan of whatever was slow, which makes debugging and testing things a lot nicer because you see what's happening. Because sometimes you run a query again, the behavior diverges, so auto-explain is super nice for this. So we continue growing, like 10 terabytes. Backup and restore, this... What is your recovery time objective for a database? Like 10 terabytes? It's like 3 hours of copying. Is that fine? Is that okay? Replication becomes interesting. If you just set up a new replica and tell Postgres, make me a replica, needs to copy all data, that can take enough time that your availability suffers. So at this size, just the inertia of the data becomes interesting. Now you might think, hey, I can split a large table into smaller tables and use partitioning. So for the application, it looks like one table, but internally it's many. That solves a few issues, and now you get a few new issues. So it does help auto-vacuum, because now every chunk that auto-vacuum has to work on is smaller, but there's more chunks, so trade-offs. You run into this issue that people set up a sequence, just, let's use an integer, which is 32-bit. Now you're in the size of like terabytes of data, which tends to be billions of things. So your sequence runs out of numbers. So then you have to somehow fix it into a big int, which is 64-bit. In the running system, best without downtime. That's interesting. There are solutions for that, but they're all not really nice. So just use big int anyway, even if you only have 12 entries in the table. Just use big int, much easier. And at this size, you tend to run into the space where auto vacuum goes into a very aggressive mode because it can't keep up, and at some point, because of reasons, it has to vacuum, so it just tells all queries to get lost. It's going to vacuum. That means you have a spontaneous downtime, usually Saturday 3 a.m. And you can't really get out of this. You need for auto vacuum to run, which takes 10 terabytes, like 6 hours maybe, which means you have a few hours of downtime, and people blog about how horrible Postgres is because they didn't really they didn't know this, and they discovered it the hard way. Now, you go even bigger, like 100 terabyte. Now, velocity becomes a really difficult thing. You're trying to just update all things that have this feature. It's going to write, maybe terabytes of data, and the wall writer is limiting how fast you can mutate. So simple things take a long time. Auto vacuum has so much to do that it can run fast enough on the primary that the replica can't catch up, which is a problem because now you can ship the wall to the replica, it's fine, but it's never going to catch up. So at some point your disk is exhausted, and that's not good. So there you run into this, how do I get out of this? You can denial of service yourself because query results can become absurdly large. And of course, you need to store that somewhere. You need to process that. And interesting. Also, many tables versus large tables gives you different pain. And if you're lucky, you have both at the same time. And so you say, hey, partitioning, that solves most of the issues. But no, I've seen one situation where the query plan took 8 minutes to create. Just a query plan creation, not executing it, just creating it, and took 20-ish gigabytes of memory because the smart people thought, hey, we partition and we partition finer. So they had like day partitions with event type partitions under it. So they had like 35,000 partitions, and the query planner is trying to figure out which of these partitions do I need. It needs about 20,000, and just figuring out, so in which order do I go through this? It gets really, really expensive. So partitions can also become a huge problem. And then you say, hey, don't care, I go bigger, like a petabyte. It's really expensive to have that much hardware, so that's not so good. At this size, I worked with not quite that big things, but the memory bandwidth becomes limiting because you have too many CPUs and not enough memory bandwidth. And that's really, really frustrating. Blast radius. What happens if this machine reboots? Just a reboot. So the whole maintenance, even scheduled maintenance, becomes surprisingly exciting because the whole thing has so much inertia, and you need to plan around this. Now you're moving like a big ocean tanker. Turning this thing around takes time. And you turn the wheel now, you're going to feel it turning in 2 minutes. And by then, it's going to have so much inertia turning that even if you counter steer, the whole thing still moves in that direction. Everything becomes very, very emotional. You need to be very, very careful and plan ahead. And everything you do, you should have an escape plan. If it goes wrong, how do I get out of here? And even if you have a single server of that size, can it handle the sheer amount of clients you want to connect to it? Because that's like, 10,000, 20,000 clients maybe? Does that even make sense? And like the whole topic of high availability, disaster recovery, backups, all this becomes super exciting, and I think we all prefer boring. So I haven't seen any Postgres instance in that size because most people figure out that you shouldn't go there, and they try to get away from it. So for me, the lesson there is there's always operational problems, and the bigger the thing gets, the more risky things get, and the less you find, for example, blog posts describing it, so you're in this weird space of, I don't know what's going on and no one can help me, which is interesting to experience, but maybe you shouldn't be there. And near the limit, you find issues that are just not really documented because the number of people who hit those issues is small. And most likely someone in AWS or Azure or Google has hit this issue and written an internal documentation on this, but you don't have visibility on that. So things go weird, and it can be very frustrating because now you're basically discovering things while things are on fire, and many emotions, not really so happy. So scaling issues. Postgres is doing MVCC, multi-version concurrency control, so it doesn't just delete the data when it's deleted. It just marks it as deleted or, no longer visible, but older transactions still see this data. So at some point, you have auto vacuum, which takes all data that is no longer visible to any transaction. And because it's no longer visible, we can mark it as deleted. So it's an asynchronous cleanup, which means you do something now and an hour later something happens. which is a bit risky maybe from the perspective that any change now might have effects later. So you do something, you go to bed, and suddenly monitoring yells at you. On large tables, auto vacuums runs a very long time, which in itself has multiple issues. So while auto vacuum is running, it has a fixed transaction horizon. So anything after that it could clean up, it doesn't see yet. So then it runs like a day, and then it has a day of stuff to clean up. And by the time it has cleaned that up, it has another day to wait. This doesn't sound healthy. So you can try to make it go faster, but then you're saturating the whole I/O system, because now auto vacuum is eating everything. And one implementation detail that gets very spicy is so the transaction ID is 32-bit, and we use basically 31-bit of that, which is the past, and the other space is basically the future. Anything that wraps around, so anything that is more than 2 billion transactions old, would time travel to the future, is no longer properly visible, and everything is broken. So what Postgres does is it has a special identifier, and in Postgres is called freezing. It marks the transaction or the transaction ID as the special value, and the data is frozen, and you're good. But that means at some point, before you hit this 2 billion limit, you need to do a freeze vacuum. So if auto vacuum is unable to run, at some point it's going to just stop everything and do this wraparound vacuum. Indexes also get really unpleasant if the tables are large, because one is the index itself gets large. Most indexes are B trees, and large B trees means you have a very deep tree, so finding a leaf takes a long time. Maybe the index doesn't even fit into memory, so you run into this issue where every index access is disk access, which is slow, which most likely makes you unhappy. So as a rough rule of thumb, I would say the practical limit is a few terabytes for a single table. If you go beyond that, pain is more pain. So the whole idea of the write-ahead log is you write summarized changes sequentially. So if the database for any reason crashes, you can replay this log and you end up in a consistent state. This is really awesome because transactions spanning multiple tables are easy, but you have a single mutex on which everything has to serialize. So you can do a lot of things, but if you actually mutate data, it has to go through the wall. So you have a single global bottleneck, and the bigger it gets, the more it bottlenecks. And replicas behave in weirdest ways, so they usually can't keep up with the primary going full throttle. So you need to figure out how to balance that in a way. The whole topic of backup is now, you're trying to move huge amounts of data. If you try to do point-in-time recovery, you need to save the whole wall stream, which at a high rate of mutation is, well, I've worked with databases that wrote over 1 terabyte per hour of wall, and now you say, hey, I want a month of retention. It's like, no, let's not go there. And even if you had that retention, can you meaningfully recover the data in a time horizon that makes sense? Because now you have to replay like huge amounts of data. One interesting pain point is the base backup, so the standard mechanism for doing a backup and for building replicas might block the cleanup of write-ahead logs. So if that takes long enough, your disk runs full. So how do you clone a replica if you can't clone a replica? I know some ways, I'm not proud of them. Restore, someone dropped a table. Oh, let's just restore from backup. How long does it take to restore that? So all of this just becomes very disagreeable. Now, the bigger the database, I would say the more clients are connected to it. So, hey, we just increase max connections. This affects internal data structures. So Postgres needs a huge amount of memory just to exist. And there's unexpected performance issues if you have very large amounts of transactions concurrently, where the transaction management, so just the overhead of saying, yes, I have finished this transaction, takes most of the CPU time of your whole transaction, which is very unexpected, and you can't get out of this. Like, oh, I add an index. No, there's nothing you can do. Just the management overhead kills you. So you can't really have that many connections. And also, every connection in Postgres is its own process. So now your operating system has to schedule literally thousands of processes. Do you think this is good? Like, are the results good? Lots of starvation and unexpected issues on that. So, hey, let's use a connection pooler, but now you have two problems. So this is generally an issue if you have too many things attached to a database. Queries. Hey, I just do this complex analytics queries. It runs for 3 days, but it's blocking auto vacuum. So that's unpleasant. Then auto vacuum has to catch up 3 days of vacuuming, and you run the next query. So we're in this weird standoff where it doesn't really do the right thing. It causes table bloat, so you have a lot of data, but it's taking even more space on disk, which can be a big issue because suddenly you need 3 times the storage space on the database server. Did you plan for that? Most likely not. You get quirky side effects with row visibility, a visibility map, weird things where an index exists, but it's scanning the whole index, and it looks like it doesn't make sense, but there's good explanations. There's good talks of people who ran into these issues, documented them, but really weird stuff happening. And if auto vacuum is stalled, it has more to catch up. So then it has more to catch up, and you run into wraparound vacuums, and there's even the amusing part where a long-running query will block most of the table mutations. So an altered table is waiting for that query to finish. Query takes 3 days. So you wait 3 days, then you actually do this, but all read queries are waiting for the altered table to progress, so your table is offline. Even on replicas you can have this, which is really great because now you can't do read queries on the replica and everyone is confused. I've seen that. It's wonderful. No one knows what's happening. It's like, but how does the replica not allow read queries? And everyone is thinking that doesn't make any sense. It did make sense. Concurrency, so all kinds of locking issues, deadlocks, waiting on locks, lock contention, so just short-lived queries, but they're all fighting for the same lock that has lots of overhead. The maximum number of locks that Postgres allows for one transaction can get exhausted. I've seen it recently because if you try to delete like 30,000 tables in a transaction, you run out of locks. Like you need a lock for every table, and this didn't work because you run out of locks and the transaction aborts, which was a bit, how does that happen? Shared buffers has a maximum size, and one weird result I have is bigger shared buffers is not always faster, because the overhead of managing the buffers can slow down queries, which kind of surprised me, but that's life at large scale. Indexes of large tables don't fit into shared buffers anymore, so now the index is slow, everyone is sad. Does failover work properly? Because now the replica might be behind by a terabyte or 2, who keeps counting? You do a failover, the replica needs to replay that, it's offline for 45 minutes until it has caught up. Are you monitoring for that? I mean, why would you even monitor that? It's not an obvious issue. If a machine literally explodes or metaphorically explodes, how long do you need to restore redundancy? Like, your replica is gone. How much time do you need to rebuild a new replica? How long does it take to restore data? It's a very sad topic because everything is full of challenges. And now suddenly you also need to think about the growth. Is your whole system designed, like, At which point are you going to exhaust the system? You grow at a rate of, let's say, 20% a month. How long until you need double the hardware? And like, oh, we should order hardware now. But we just ordered hardware. Yes, that's why we need to order hardware. Those were interesting discussions because exponential functions are not intuitive for most people. So they're like, but we already did that. Yeah, but you need to do it again and faster. So now, if you actually have these issues, you do specialization if you can. So for example, you disable fsync because it just slows you down. You use unlocked tables because if there's a crash, then whatever table is gone, don't care. Some problems allow this, not all of them. Maybe you disable auto vacuum because you have an append-only workload and only do that per table space, don't do it globally. I can explain later. Maybe you can do batch inserts and vacuum, then auto vacuum has less to do. But now you don't have an interactive workload anymore. If you can do that, it's great. If not, then, well, you can do partitioning, and instead of deleting data and causing lots of work for auto vacuum again, maybe you can just truncate or drop a partition, and maybe that's a lot easier. Because replication gets weird at this high velocity, how about we double write from the application, and like that we don't need to worry about that. I've seen people do that, and it made sense because replication wouldn't have worked. But there's like these trade-offs between like convenient and fast. The faster you want to go, the more pain it has. And like cost and complexity are also like, you want it cheap, it's going to be horrible. A bit more money can make it a bit less, yeah. But then there's the question, do we have the budget for that? Do we have the manpower for that? Should we even have all this data? So of course, you know, there's like, where are we going? What's the future for us? There's a chance that different storage engines help. So for example, OrioleDB doesn't have the auto vacuum problem. That's great. It just doesn't do linear scans nicely. So you trade one thing for another. Columnar storage is very popular. It has some advantages, but it also does write amplification like nothing else. So, does it work? There's great improvements in the like sharding, the query planner, for example. Timescale has done some interesting work. It solves some of the issues, but not all of them. And there's always this discussion, maybe 64-bit transaction IDs mean we can skip this whole vacuum topic for a bit longer. It's been a discussion for years, and it's still not in mainline Postgres. But you know, people are working on improving things, and maybe we can grow a little bit more. Of course, we can just go distributed Postgres, and there's Greenplum and Citus and Postgres XCXL. They're both kind of unmaintained. That solves some of the issues, but gives you some new issues. There's Postgres front end, but everything behind it is different. For example, CockroachDB and UGabyteDB. Now you're not running Postgres. Like your application doesn't need changes, but you need to learn a completely new system. And you learn maybe some interesting new issues. There's like this whole auto-scaling cloud-native stuff. NeonDB has built some interesting things. I have no strong opinions about that because I haven't really found a use case where that is important. But maybe it solves your issue of this specific, I want to store this specific type of data. But we also have like these amazing things, foreign data wrappers. Like we just store it somewhere else, like in Parquet files, and we use Postgres just to use the files like a table. It's one way of doing it. We store all the data in Elasticsearch and use the Elasticsearch foreign data wrapper. Trade-offs. I mean, and now you're storing data somewhere else. You need to get the other thing to scale. It doesn't really solve your issue. You just shifted it somewhere else, and it's someone else's problem. So lots of extensions that add missing functionality, that can be really great because by doing something more complex, maybe you can improve how you process the data. Or you just put another DB inside Postgres, like pgduckdb, and there's an SQLite extension. So just put the data in SQLite, and maybe that helps you somehow. Maybe, I don't know. But there's all these options, this potential, and maybe it does the thing. But I'm going down the path of maybe we don't need to save all the data, or maybe we don't need to keep it forever. Like if we expire after 30 days, then we don't need to store all this historical data forever. Maybe that helps us. So most of these issues, maybe we just don't want to have them, and we just figure out what data we actually need and don't store the rest. There's this beautiful German word, Datensparsamkeit. So just be frugal. Don't use, like, you can use the data, but then you discard it as soon as you can, and that means you don't have this pile of stuff. But you also need to think about the budget. Data has costs, like purely financial costs of storing it, of accessing it, of processing it. Compliance, huge topic. Who has access to what data, provenance of data, where does it come from, where does it go? If you don't have the data, you don't need to care about compliance. So, and of course, you need a lot of manpower to just keep the thing running. And then you want new features, you want to grow the thing, so you need more people. It's difficult to find people, it's difficult to retain people. But if you don't have the problem, you don't even need these people, so it maybe saves you. And at scale, sometimes you just need to build a thing because no one else has published anything that does it. And if you want to go down that path, you need to build it, you need to own it, you need to handle the whole life cycle of it. And I think most of us don't really want to do that. And with that, I'm basically at the end of my talk. Are there any questions, remarks, ideas?
Have you used huge tables in Linux to mitigate the problem of the too many handles for the...
Yes, huge pages in Linux. Yes, it gives you a measurable, consistent speed up. There's a few quirks around it, but in general for Postgres you can enable huge pages, and it just does the right thing basically. It gives you a measurable speed up of 10 to 20%, but it's not that massive. It is benchmark visible, it is definitely a speed up, but it's not going to help you if your database runs that slow. It's yes?
What's the type of data usually occupies this hundreds of terabytes or petabytes in your case, in your practice?
So I was mostly involved with systems that were basically, you have some application that's creating events. Like, for example, you have an SDK that people integrate into Android applications, and when they install, it sends an event. When they uninstall, it sends an event. In a game, if they finish the tutorial, it sends an event, so you get many events, millions users, so you have billions of events, and everything is just big number.
Okay, I suppose that the answer will be that you store a big number of events in Postgres. And the follow-up question is why using Postgres for storing a big number of events if other specialized databases for analytics such as ClickHouse exist, or DuckDB.
Okay, ClickHouse, for example.
DuckDB.
ClickHouse has this wonderful ClickBench. ClickBench demonstrates that memory is faster than disk. Anything else doesn't matter.
I disagree with you.
But if you look at the benchmark setup, ClickHouse compresses the data so it fits into RAM. So ClickHouse reads the data from RAM. Everyone else doesn't fit into RAM, so they read from disk. So you're comparing how much faster is reading in memory.
When we are talking about ClickBench, yes, I agree with you that ClickBench benchmarks performance of reading and writing in memory. But when we are talking about ClickHouse, which can handle petabytes of data.
I've worked with a huge
on systems with gigabytes of memory, and it handles this data much more efficiently compared to Postgres because of compression, because of column-oriented storage, and because of partition and other things.
Kinda, yes. But for example, I made this joke earlier, and then we disabled fsync. That's what ClickHouse does. If you try to enable fsync, when I tried it last time, it crashes because that code path hasn't been tested. So, I mean, yeah, it's one way of doing things.
Okay.
The other thing is ClickHouse organizes data by primary key, so you can only query by primary key. So anytime you try to do basically a query that goes by another column, you need to read the whole thing. So you do a sequential scan, which is kind of not really good. So in Postgres, I can add an index on every column if I want, and every column has the same speed up. With ClickHouse, there's one fast path and everything else is weird. And then the interesting feature of ClickHouse is that it materializes the results in memory. So the maximum result size that you can have is limited by your RAM size, which is kind of, with lots of data, like interesting choices.
Yeah, I see. But when you were asking the question, which amounts of data have you experienced with, and I raised the hand that I had experience with hundreds of terabytes and petabytes of data, and that's my experience with ClickHouse exactly, and it works. I had some problems you mentioned in your slides, but the number of such problems is much lower was in ClickHouse compared to Postgres, because I migrated from Postgres to ClickHouse, and this saves me
so this is basically specialization. If your workload allows that, if you have just exactly this type of query, yes, definitely ClickHouse is going to be faster. But most of the time, I don't do time series data, and I want to slice by multiple dimensions, and their ClickHouse pretty much doesn't work. And I've worked with a huge ClickHouse cluster, like hundreds of petabytes. And let me put it this way. I would prefer not to ever work with ClickHouse again, because it's just not giving me happy emotions.
The same you can say about Postgres at hundreds of petabytes of data.
It's a different pain. Like Postgres still has like this transactional thing going on and all that. It depends on what you're doing. So for some workloads, definitely, even SQLite is, better in quotation marks because it fits the problem better. But for example, you say we want to use Postgres because that's what we commonly use. Then you need to figure out how to scale Postgres, and then you learn all kinds of horrible things. And if you go big enough, all databases fail in some way. So you have the trade-off, how do you want to fail? Any other questions? No?
No more questions? Then, just a second.
Slide 22.
Okay, slide 22.
Yeah, very quick question. You had an asterisk by the 1 to 2 gigabytes per second, but it doesn't say what it is.
Yeah, it's basically, if you write, for example, a very large objects, then you don't need... So what I usually see is relatively small updates. So every, let's say, 8 kilobytes, you do an fsync. So this is very limiting. If you do larger transactions, then you have less fsync. So in theory, you can go faster. So it kind of depends on the workload. But most of the time, what I'm seeing is like, you can really go faster than this. And it's very rare that you have like this specific pattern where it could go faster. I mean, it also depends on the hardware. If you have a faster CPU, maybe it goes faster. If your memory latency is lower, maybe it goes faster. So this is just like first order approximation. And always, do your own benchmarks, because the results you see might be totally different than what other people do.
But you can run two instances of Postgres on the same machine, and they will give twice.
Yes, you can run multiple instances, but then you have some kind of sharding. And I mean, we've done that. We had like 10 Postgres instances on one server, because it was easier to not use RAID and instead like use one Postgres for each disk. And if a disk dies, it's one Postgres gone and not the whole thing affected. Does it make sense? Is it what you want to do? I don't know. At that time, it seemed like a good set of choices, but it had some operational unhappiness. So, you know, the trade-offs. You need to figure out what you can tolerate and you know, what does your budget allow, what does your staffing allow, and I don't want to be prescriptive and say this is the right way. There's just, most of the time this is good, but here we're in uncharted territory, so you know, we can have a discussion about that, we can figure out requirements, but I'm not going to declare like this is the right way.
I think we have to end it there for today.
Okay.
So we can
if
go to
anyone
the next.
wants to talk to me,